okay? All right, so let's look at how all of this ties together, which is your section 7, your hand analysis for the common source amplifier. So the hand analysis is going to give you what your approximate gain can be for that amplifier, all right? So you must hand calculate GM, so GM of the PMOS, 2I over VOV, GM of your NMOS, 2I over VOV. So again, this is showing you that if you picked your VOVs to be equal between the two, your GMs would be equal, but when you're in simulation, those will be probably slightly different. So I can hand calculate this as 2. I set my current to 60 microamps from the previous section, my 0.1 volt VOV, and I get 1.2 milliamps per volt. And I will get the same value for my NMOS because they have the same current going through them, and I designed them for the same overdrive voltage. So I will again have 1.2 milliamps per volt. Okay. I can also calculate the R naught of the devices through hand calculations. So my R naught of my NMOS device, 1 over lambda ID, where lambda is found in part 1. In part 1. And so I made the assumption, you find it in part 1, I'm making the assumption it's 0.5 just for sake of this discussion. Okay, so I can say it's 1 over 0.5 if I'd like times my current. Okay, and you can find a number for that. R naught P is 1 over lambda ID, same ID. Again, you find the lambda of the PMOS and NMOS, I'll call them lambda N and lambda P because they're not equal. So again, you will find this through part 1, and you have your current 60 microamps. So I'm just going to right now call it microamps. I'm going to call this just I'm going to leave it as lambda P, and you'll find some number, okay? So I was making the assumption lambdas were 0.5, but to be honest, for this analysis, I don't need actual numbers here. I just want to show you guys what happens to the gain of this system. Okay, so in order to find the small signal gain, which is a part of our hand analysis, we are going to need our small signal model. So again, we don't have to assume now, we have set our devices to be in saturation, right? We know that by our DC bias, and we can calculate the R naughts and the GMs, which are always our first step of any hand analysis, any small signal hand analysis. And then we're now going to take all of our transistors and replace them with their small signal model. So we only have 2 transistors, and the NMOS and PMOS. So starting with the NMOS, I'm going to have my source voltage here, and that's tied to ground. I'm going to have a VGS of my NMOS to my gate. I'm going to have my GM, VGS, and I'll say that's N. I'll call those all N since the GMs may not be equal. I have the R naught of my NMOS, all right? And then that is tied to my PMOS device where the drains are tied together. So doing my PMOS now, excuse me, the current's going in this direction. I have my GM PMOS, VGS P, R naught of my PMOS, tied to ground. And then I'm going to have a VGS of my PMOS device somewhere over here. I'll just say VGS P, and that would be the gate of the PMOS device. All right, so let's look at where the gates are connected. The gate of my NMOS device is my input signal. So that's where I'm going to put V in. And the gate of the PMOS device is tied to a DC voltage, right? Only a DC voltage. It's my active load, so VGP. So in small signal analysis, that is ground. Okay, so starting at, I want to find small signal V out over V in, should say, and this here is my V out node, right, in between the 2 drains. So starting with the V out node, I can write my KCL equations. And so I've got V out, the current going through R naught over R naught N, plus V out over R naught P, that's a current going through R naught P, plus GMN times VGSN, plus GMP times VGSP. Those are the 2 voltage control current sources. And all of those currents summed out of that node equals 0. So if I look at, I've got one equation with V out and VGS's. If I look at VGSP, and I can write an equation for VGSP, which is actually you've got a ground at your gate and a ground at your source. So VGSP is actually 0. So this whole term will go to 0. And VGSN, if you're looking over here, is actually just VN, right? The source is ground, the input is at the gate. So VN. So I can replace this VGSN with VN. And now I can solve for Vout over Vn. So rewriting that equation, Vout 1 over R naught N plus 1 over R naught P plus GMN times Vn equals 0. So Vout over Vn, which is my small signal gain, is equal to minus GM of the NMOS R naught P in parallel with R naught N. That's what I will come up with, rearrange these terms, okay? So you can see, it depends, the small signal voltage gain depends on the GM of the NMOS device, not the PMOS device, that's only the load, and the output resistance of both the PMOS and the NMOS devices, okay? So for the sake of this analysis, let us assume that R naught P is equal to R naught N. Just for our analysis, for my discussion. This is not the case for you in your analysis, but for my discussion, I want to observe what happens. Let's assume the R naughts are equal. Then my voltage gain would be approximately GM and times R naught over 2, where R naught's both of those, right? And if I look at then what GM and R naught are equal to, well, GM is 2I over VOV, right? And we know that R naught is 1 over lambda I. Okay, so let's plug those in. We're going to have minus GM, minus, let me write that, minus 2I over VOV times, okay, the 1/2, fine, times 1 over lambda I. If you look at this equation, the currents cancel, well, the 2's will cancel for this case, and I would have minus 1 over lambda VOV. The lambda is just the phase shift, right? So if you look at this voltage gain, you see that the current has been taken out of the equation. It is not dependent on your DC bias current, okay? So this is showing that your gain is not dependent on your DC current bias, right? What does it depend on? Well, it depends on the lambda, which is a process parameter, and it depends on your VOV. So if you want the gain to go up, you need to make your VOV smaller. Okay? And in your lab, this VOV was given to you. So that you fixed this VOV at an actually pretty small value. 0.1 volts is a very aggressive VOV, meaning a very small VOV. And so by fixing this VOV, you have in essence fixed your small signal gain for a particular process and a particular length device. Your length was also fixed at 300 nanometers. Okay, so if you get to your lab and you realize you don't have enough voltage gain in simulation, you do your hand analysis, you derive your hand analysis, you derive your voltage gain, and you see I don't have enough voltage gain, going back and increasing the current through the circuit is not the way to get more gain. Instead, go back and reanalyze your gate to source voltages for your PMOS and NMOS devices and make sure that you are fulfilling your overdrive voltage criteria. So by giving you an overdrive voltage in this lab, we in essence have fixed a small signal gain for you. So if you don't have accurate or the correct DC bias on the transistors, you will not get adequate gain. So go back and check your DC biases if you end up with a problem with gain. Okay, look at where those devices are actually sitting. Are you actually achieving an overdrive voltage of 0.1 volts? Okay, so in essence, through your DC analysis in this lab, you have found a small signal gain, or you have set a small signal gain. Okay, so that's how they correlate to each other. All right, so for an example, for my example, I said assume my lambda was 0.5. That was my lambda. Your lambda, of course, is different. Then my small signal gain would have been 1 over 0.5 times 0.1, which is 1 over 0.05, absolute value. So it would be inverting. So I would get a gain of approximately 20. And 20 log of 20 is 26 dB, which is my spec. Okay? You should have no problem getting the DC. Actually, as a matter of fact, your small signal gain will be higher than this 26 dB value in your circuit if you choose the correct DC bias and your correct width. Okay, so as long as you're biasing correctly and you've chosen a width based on your calculation from your DC analysis that we just did, you will have over 26 dB gain easily in this circuit. It is okay to have higher than 26 dB gain. So you do not have to set your gain to be exactly 26. The spec was a minimum of 26 dB. So as long as you are over 26 or at 26, you are fine. Okay, don't try to tune your circuit to get exactly 26 dB. No need to do that as long as you're over the 26 dB. Okay, so that concludes our discussion for Lab 4 material. Please go through and do the analysis yourself for all of these values. You will be finding lambdas in part 1, and from those lambdas, all of these equations will have slightly different values. This was a discussion for your information, but I would like you to repeat this for your Lab 4 deliverables. Okay, and so remember in Lab 4 part 1, when you are finding the lambda of your device or the early voltage, the motivation for doing this in the end is to find your output resistances, because your output resistances are dependent on channel length modulation. Okay, so please keep that in mind. That is why you are doing part 1 of that lab, plotting those IV curves and finding from those IV curves early voltage, lambda, and hence output resistance R0. Good luck.